So 6.3, we're going to look at how we can start proving that triangles or that quadrilaterals are parallelograms. And in order to do that, we're just going to look at certain conditions that we know are true about parallelograms and see if that's enough for us to formulate a proof that it is in fact a parallelogram. So, first thing we know about parallelograms, aside from the definition, because of course if we get the definition to be true, so if we know that two opposite sides are parallel, then we know it's a parallelogram by the definition of parallelogram. But let's say we don't know that they're parallel. Let's say we know that the opposite sides of a quadrilateral are congruent. Well, is that going to be enough for us to say that it's definitely a quadrilateral? In other words, if we know that, can we prove that opposite sides are parallel, which would be the definition? So let's take a look at what this proof would look like. And what we're going to be using here is we're going to be using some diagonals in order to finish this proof. Okay, so I'm going to put both my diagonals in here. Now, what I'm given is that opposite sides are congruent. So my proof, that's going to be my given. That's going to be the first thing I start with. So let's call this A, B, C, and D. So I'm given that AB is congruent to CD. I'm also given that AD is congruent to BC. Okay, because that's also a set of opposite sides. So these are my givens. Well, these are congruent. Let's see. I'm also going to have some vertical angles. Okay, so I can do that. That's going to be off here by itself. I guess I need another letter here. So we could put this as E. Okay, E will be our middle point there. But just by looking, that's only going to give me a side and an angle, okay, in all these triangles. And I'm not going to have enough information to get anything else. So I really don't think that is that helpful. So what I'm going to do is I'm going to ignore one of these diagonals for now. And I'm just going to look at these two big triangles here. Okay? If I do that, I can mark this side congruent to itself by the reflexive property. So I can say AC is congruent to itself. From reflexive. These three things lead me to say that triangle ABC is congruent to triangle CDA. Okay, by side, side, side. Which then allows me to say that this angle is congruent to this one by CPCTC. Let's give myself a little more room here. So I can say angle BAC is congruent to angle ACD by CPCTC. I could also say that this angle is congruent to this one for the same reason. This angle DAC is congruent to angle BCA by CPCTC. Now I've just proven that some alternate interior angles are congruent. Okay, so these angles here are alternate interior to the top and bottom lines. So that tells me that AB is parallel to DC here, these angles are alternate interior on the side lines. So that allows me to say that AD is parallel to BC. Okay, both of these are by the alternate interior converse. Okay, same reason here. So having opposite sides congruent does in fact allow me to say that the shape is a parallelogram. So from now on, you don't need to go through all these steps again. Anytime you have opposite sides that are congruent, you can skip right to the end of this proof. Okay, the end being that shape A, B, C, D is a parallelogram by the definition of parallelogram. All right, so that is one way. This is one way to prove that a shape is a parallelogram. So on our front page, we're going to want to put that in. Okay, we want to go back here and see. If I have a quadrilateral, one way to get that quadrilateral to be a parallelogram is if opposite sides are parallel. The next way we just figured out is if we can prove that opposite sides are congruent. Okay, so if I have a four-sided shape whose opposite sides are congruent, I know it's a parallelogram. Okay, let's continue on to the next one. Give myself a little more room here. If opposite angles of a quadrilateral are congruent. So we'll start with our four-sided shape. Okay, and they're telling me opposite angles are congruent. This one we can do an algebraic proof. Okay? A, B, C, D. Well, if opposite sides are congruent, and I have a four-sided shape, I know that the measure of angle A plus the measure of angle B plus the measure of angle C plus the measure of angle D should equal 360 degrees. And I know that angle A and C are congruent, so I can substitute. So I can say the measure of angle A plus the measure of angle B plus, I'm going to substitute the measure of angle A again for angle C. So the measure of angle A. I'm also going to substitute B in for D. So if I combine these, I'm going to have 2 times the measure of angle A plus 2 times the measure of angle B equals 360 degrees. If I divide everything by 2, okay, divide all these by 2, I'm going to get 1 measure of angle A plus 1 measure of angle B equals 180, which means that they are supplementary. So A and B are supplementary. These are consecutive interior angles on the sidelines. So since I have supplementary consecutive interior angles, that would tell me that AD and BC are congruent. And if I went through and instead of substituting B for D, if I instead substituted D in for B, I would have D and 2D, and I would find out that A and D are also supplementary, which would give me these lines parallel. So, and that's the consecutive interior converse from chapter 3. What we now have is, if we start with opposite angles that are congruent, we now know that that is indeed going to guarantee that we have a parallelogram. So this gives us another reason on our front page. Okay, so our next reason is if opposite angles are congruent. So anytime you have a four-sided shape whose opposite angles are congruent, that guarantees you have a parallelogram. That's another way to prove you have a parallelogram. Next way. So let's say one quadrilateral of or one angle of a quadrilateral is supplementary to both of its consecutive angles. This one, we pretty much just went through the proof, okay? So what we're saying is if A, it's supplementary to both of its consecutive angles. Okay, both of its consecutive angles would be B and D. Well, we just saw that if A is supplementary to angle B, that proves that these lines are parallel. If A is supplementary to D, that proves that these lines are parallel. Okay, so that's kind of just another way to use, we don't need opposite angles congruent, but it kind of comes from the same proof, so we can fill this in. Okay, one angle is supplementary to both consecutives. So to both consecutive angles. That's another way to prove they have a parallelogram. Okay, now there's one more way to do it. All right, we've covered all the properties of parallelograms: opposite sides congruent, opposite angles congruent, consecutive angles are supplementary. Actually, there's two more, I guess. So let's put another line. We're going to need another one here. Okay, so make sure you draw that extra line on yours, because there's actually two more ways to do this. First one is, we know that the diagonals of parallelogram bisect each other. So let's say we start with that. Is that going to be enough for us to prove that the quadrilateral is a parallelogram? I'm sure you've guessed by now that it is going to be enough. But let's just go through the proof. This is good practice for you for proofs. So if these diagonals are bisecting each other, I know these two parts are the same and these are the same. I'm going to have some vertical angles here. So if you can see, I'm going to have this triangle congruent to this one, and this triangle congruent to this one by side angle side in both cases, which is going to allow me to say that this angle is congruent to this one. Okay, and that would give us these lines parallel. I could also say that this angle is congruent to this one, which would give me these sides as parallel. Okay, so I kind of went through it quickly, but you should fill in a good flow proof for this. So put some letters in here. And you're going to need this middle one, okay, so we'll call that E. And you're starting with AE congruent to EC. And you're also starting with DE congruent to BE. See if you can get a good flow proof that ends with you saying that the opposite sides, so your last step should be that AB is parallel to DC, and you should also be able to say that AD is parallel to BC. Okay, so see if you can fill in the middle part of that flow proof. That'd be good practice for you. So that's another way. We'll fill that in, but let's get to the last one. The last one is not a direct property of parallelograms, but it is just an extra way that we can prove a parallelogram. Okay, and that's if we have one side of opposite sides, or one set of opposite sides that are both congruent and parallel. Okay, and for this one, we're just going to look at another diagonal. Since these are parallel, I'm going to get alternate interior angles. I'm also going to get a reflexive side, so I'll have side angle side for these two triangles, which lets me say that these angles are congruent as well as these angles. And then again, I'm going to have alternate interior for the side lines here. So those will be parallel. So we can fill in that last line now by saying that if we have one set of opposite sides that are both congruent and parallel, that's enough to go from a quadrilateral to a parallelogram. So the one that we had before this was if the diagonals bisect each other. So the diagonals bisect each other. And if you have one set of opposite sides are parallel and congruent. So these are the 6 ways to prove that a quadrilateral is a parallelogram. So you can be expecting to have some proofs using this. Make sure you remember all the things that we used for proofs before, you know, vertical angles, the segment addition postulate might come in, alternate interior angles, all that stuff, as well as your base angles theorem, your perpendicular bisector theorem. So if you have a point that's on a perpendicular bisector, it's equidistant from both endpoints of the segment. All that stuff can be used in these proofs now. So let's look at some example problems from this section. So what value of x and y will make the polygon a parallelogram? Well, let's see. I know that in order to be a parallelogram, opposite sides need to be equal or congruent. Or I could say that the consecutive sides to one of my angles have to add up to be 180. So 2 options here. One option, I could use opposite sides being equal, or opposite angles being equal. So I could say 2x has to be the same as 70, which would mean that x would be 35 degrees. Then these have to be equal also. So 3 times 35 is 105 plus 5 has to equal 35 plus 3y. So this is 110 equals 35 plus 3y. Subtract 35, and I get, let's see, that'd be 5. And then 75 equals 3y. Divide by 3 and I get 25. So my answers would be 35 and 25. If I go a different route, 3x plus 5 has to add up with 70 to be 180. And that's going to be 3x plus 75 has to equal 180. Minus the 75, I'll get 3x equals 105. Which means x is 35 again. And then I could plug it in here, or I could use this one here. I know that x plus 3y plus 70 has to equal, plus, yeah. So the 2 angles added together. So make sure I've got supplementary. Okay, so I've made sure these are supplementary. Now I need to make sure these are supplementary. So subtract the 70 over, that's 110. This is actually 35. If I subtract that over, I get 75. So 3y equals 75. So y again is 25. And now I've just shown that 70, this angle, is supplementary with both of its consecutive angles. Okay, so 2 approaches using two different ways to prove that a polygon is a parallelogram. Let's look at the next one here. In order for this shape to be a parallelogram, I need these diagonals to bisect each other. So that means I need 3x to equal 12. I need x plus y to equal 5y. This one I can solve first. So x is 4, which means I can put 4 in here. Subtract the y. So 4 equals 4y, so y equals 1. That would be my answer for this. All right, here's what we'll end up doing more often than not is proving parallelograms from points. Okay, and there's different ways you can do this. We can use any of the 6 methods. So let's take a look at the ones that will lend themselves more easily to using points. Okay, opposite sides parallel. Okay, I can do that one because in order to show the opposite sides are parallel, I just need to know their slopes. If they have the same slopes, then that means they're parallel. Opposite sides congruent. I can do that one pretty easily because I can use the distance formula on my opposite sides to make sure they're the same length. Opposite angles congruent. That one's not so easy with points because we don't have a way to figure out what angles the points are making yet. One angle is supplementary to both. Again, I don't really have a way to do that with points yet. We'll get to that when we get to some trigonometry. Diagonals bisect each other. That one will take some time because I'd first have to find the intersection point of the 2 diagonals and then make sure that I get 2 congruent pieces. So that one's going to take a while, and I don't really want to do that. One set of opposite sides are both parallel and congruent. That one I could do because, again, slopes and distance formula. So we're going to stick to these. Opposite sides parallel or congruent, or one set of opposite sides are parallel and congruent. So let's go through and look at how we do that. So if I've got these points, and I want to prove that's a parallelogram. All right, so I want to prove that PQRS is a parallelogram. Well, I'm going to look at each side, PQ, QR, RS, and SP, and I'm going to look at their slope and their length. Okay. So slope of PQ, I'm going to subtract my y, so 3 minus 2 is 1. Negative 1 minus 4 is negative 5. The distance here, okay, we can use distance formula. Okay, which means I'm going to subtract my x values, square it, add it to the difference of my y values squared. So if I take and subtract my x values, negative 1 minus 4 is negative 5. It's negative 5 squared. 3 minus 2 is 1, 1 squared. Here we get 25 plus 1, so I get the square root of 26, which would break down to 2 and 13, so nothing comes out. So that's simplest radical form. Let's look at QR, the slope. I'm going to take 2 minus negative 1, which is 3. And I'm going to take 4 minus 1, which is also 3. So I get a slope of 1. I'm going to take distance. So if you notice, I'm kind of going to get these same numbers because I'm subtracting in both cases. So I'm going to take 3 squared plus 3 squared, square root it. So that'd be 9 plus 9, which is 18. So I get the square root of 18, which is 3 times 3 times 2. So I get 3 square root of 2. That's the length. Now let's look at RS. Negative 1 minus 0 is negative 1. 1 minus negative 4 is 5. If I do the distance, I'm going to get 5 squared plus 1 squared, which is the square root of 26. If you notice, PQ and RS, they have the same slope. So at that point, I know they're parallel. They have the same length, so I know they're congruent. And I could really stop right here because I have one set of opposite sides that are both parallel and congruent. If I hadn't been doing the length, I would need to keep going one more to get both sets of opposite sides parallel. So SP, 0 minus 3, or we could go 3 minus 0. Negative 1 minus negative 4 is going to be positive 3. So again, I get a slope of 1. I'm going to get the same distance here. All right, so no matter which route I decide to choose, if I only did slopes, I can see that opposite sides have the same slope, which means they're parallel. Okay, 1, 1, negative 1/5, negative 1/5. I can see that opposite sides are congruent because they have the same length, so that would be enough. Or I could pick one set of opposite sides and show that they're both parallel and congruent. So these are the steps that you'll be taking to use points to prove that they are the vertices of a parallelogram.